Okay, let's pick it up at chapter 14, acid-base equilibria. We had already started the chapter, so this first lecture is just going to be a review of what we did to kind of catch us back up, since it's been a while since we met. The first thing I want to point out is the review sheet that I gave you. Oddly enough, I gave you the cheat sheet for all of the notes for the entire chapter right up front. And so basically what I will do for the remainder of this chapter is to explain what all of this means. We started out by looking at definition of acid bases, and you learned that there are three basic definitions. An Arrhenius acid is one in which a proton is donated in water and a hydroxide is donated in water when a material is placed in water. That was the original definition of an acid. The definition was broadened a little bit by a group called Bronsted-Lowry, in which they left hydrogen, an acid as a hydrogen donor, but described a base as anything that accepts a proton. And finally, a Lewis acid and base is the most general, and it defines it in terms of something that accepts a lone pair or something that donates a lone pair. And some common examples, car batteries, Drano, baking soda, vinegar, those were given as common examples of acids and bases. There's just a tremendous amount of acid-base use in both industry and the human body. Just some of the real preliminary information. For every acid, there is a conjugate base. A conjugate base is basically what's left after an acid loses one proton, not two, but only one. So in this case, HA and anion A- would be considered an acid-base pair. And there's some acid-base pairs for some real live acids. Hydrofluoric acid, sulfuric acid, and also there's bisulfate. It can go to sulfate. So both of those are acids to be discussed in a minute. Let's see what we have here. Here is a generic kind of symbolism, a simple way to show the acid-base, conjugate acid-base pairs, and the reaction in which an HA loses an H plus that goes to A minus. And it's a loop. The A minus, the anion can gain a proton and go back to the acid. So you oftentimes in the real world have this loop that's going around and around. Let's talk about it. Most of these occur in water. That's the most common medium. And so water actually plays a role in it. What really happens is the way, first of all, how it's portrayed in the textbooks. An acid gives up a proton and thereby generating an anion. And so because we know this sets up an equilibrium, you know that the equilibrium constant is the concentration of your products divided by the concentration of your reactants. And because it's an acid, we call it Ka for acid. Sometimes we actually cannot use this shorthand notation. It's preferred, but sometimes we have to show the role water plays. And what really happens in this reaction is a proton isn't really generated. What's generated is a hydronium ion. What is that? That when the acid gets rid of this proton, something really has to accept it. What usually accepts it, if you're in water medium, is water. And so technically you don't really generate an H plus, you generate an H3O plus. And so this is called a hydronium ion. But usually this shorter abbreviated version works out, and it's much, much cleaner to use. At any rate, the Ka for an acid can be expressed using either one of those equations when water is the solvent. Water, let's talk about that. So water autoionizes. It forms ions all by itself. And this is very important because we know in a complex mixture, no matter what, if Mother Nature wants a Ka, an equilibrium constant, she will do it no matter what else happens in that solution. She will establish that equilibrium constant for that particular reaction. And it just so happens water has one of those reactions that always occurs. One water can actually bump into another water to produce a hydronium ion and a hydroxide ion. So here we have water acting as an acid. It generates a hydronium ion, and it also acts as a base. It's generating a hydroxide. So let's look at the equilibrium for that. So the Ka for that. Now because this is water, we're going to now change the A from acid to W to water, noting specifically that we're talking about water. And this is really, really critical because Kw will be used a tremendous amount of times when you deal with aqueous media. So Kw is equal to H plus HO divided by water, but because water is a pure substance, we can ignore that. In other words, the activity is 1, leading to Kw is equal to the H3O plus, HO minus concentration, and that is equal to, measured under normal room temperature circumstances, 1 times 10 to the minus 14. And so there you have it. If you have a glass of water, there is going to be a little bit of acid and base in it. But how many of these water molecules undergo this change? Well, if you look at 10 to the minus 14, it's a pretty small number. That really means 1 in every 100 billion water molecules actually breaks apart. Not much, but it's nevertheless very, very important, especially where biological systems are concerned. By the way, we do know that equilibrium constant is a function of temperature, and we will just show you at 25 degrees C, you get your 1 times 10 to the minus 14th. But if you go colder, if you're colder, the Ka is actually going to drop a little bit. And likewise, if you get warmer than 25 degrees, the Ka for water actually goes up. In other words, you take a cup of warm water, if it's pH 7 at room temperature, if you have a very accurate pH probe, you'll find out at 60 degrees C, the pH is actually higher than that. The hydrogen ion concentration is higher than that. Okay, now we've talked about water and we've talked about acid. Let's talk about the two together. So what happens is an acid will donate a proton to the water, and that's where we get the hydronium ion information. Again, for any acid, you can use the shorthand version or you can show the hydronium ion present. There's also this organic chemistry type of scheme that you can show. The acid donates a proton, but in this case, I've shown what it donates it to. I've actually added a layer here and said this donates a hydrogen to water, and now the water goes to produce a hydronium ion, and the acid goes to an anion. Likewise, oh, by the way, this is what makes it an acid. It is not an acid because it's HA. It's an acid why? Because it donates a proton, a hydronium ion, when put in water. And this is not a base just because it's A minus. The minus is not what makes this a base. What makes it a base is the fact that when this thing with a minus charge hits this water, it then produces what? A hydroxide group. And that is the definition of a base. So here we go. We've talked about the abbreviated version here, so let's move on to the next slide. Okay. Amphiprotic species. It's an acid. No, it's a base, right? Okay, so there are some things amphiprotic. We know water is amphiprotic. It can act as an acid and a base, but water is not the only thing that is amphiprotic. For example, bicarbonate, that is carbonic acid that's halfway to the carbonate, is called bicarbonate. Bi meaning halfway. It's halfway there. It's lost one of its 2 protons, or at least it's partially there. Okay, so here we go. So H2CO3 can only be an acid. It can donate a proton and form the bicarbonate. So this is an acid. Carbonate, on the other hand, can only be a base. It can't give up any protons. It can't be an acid, but it can absorb a proton and become a base. But look at bicarbonate. It's amphiprotic. Why? Because it can gain a proton and form an acid, or it can lose a proton and become a base. So it can be both. It can go from a base to an acid, or it can go from an acid to a base. It is amphiprotic. And as we've already seen, of course, water is amphiprotic. So one of the questions that we covered was, which of the following could be amphiprotic materials? And the answer is, let's see, this one can't be because it can only donate, this is nitric acid. It can only donate a proton. It can't accept a proton. There is no such thing as H2 NO3. This, right, acetic acid, it can't. It can donate a proton, but it can't take a proton because there's no such thing as CH3CO2 H2. This one's different. This one can take a proton and become H2SO4. That's a real material, sulfuric acid. And likewise, it can lose an H+. It can just go to plain old sulfate. So this is amphiprotic. Likewise, this acid can only lose protons. It can't gain it. And this base, perchlorate, can only gain a proton. It can't lose it. So your answer is this is the only amphiprotic species in that list. Moving along. These numbers get awfully big and awfully small. For example, 10 to the minus 14. It gets really tedious dealing with very, very small numbers. Or sometimes very, very large numbers. So what we decide to do is just look at the power term. That will tell you. Anything raised to the 10 to minus 14 is very, very small. So the way we key on and just talk about things in terms of the power term is this function called the log. So by definition, the minus log of anything is called the P of that thing. For example, Px, where here x is some generic term, is what's called minus log x. Or rather, I should say minus log x is called Px. Now, x can be anything. If it's a hydrogen ion concentration, then the minus log of hydrogen ion concentration is called pH, and that's where that comes from. And if you take the minus log of the hydroxide concentration, that's called POH. Or if you have an equilibrium constant, that's a very big or very large number, and you take the minus log of it, that's okay. We're just going to call that pK. There. It's just a simple mathematical deal. Nothing more complicated than that. pH versus POH versus pKW. These are the big things we have. Earlier, we know that KW is equal to the protons plus anion concentration is equal to 10 to the minus 14th. If I take the minus log of everything, and let's see, I want to take the minus log of this, and I'm going to take the minus log of this, and I'm going to take the minus log of this, and then I'm going to do my math. The minus log of that is called pH, the minus log of that is called pH, and the minus log of that is called 14, and the minus log of this one is called pKa or pKw if you're talking about water. So there we have another very important equation. pH plus POH is equal 14. And kind of to bring it all together, the things that we've kind of learned here is we're going to deal with four main types of variables that are typically asked of questions. Ground zero is H+. We typically want to know what the hydrogen ion concentration is. Oftentimes, they don't want to know what the hydrogen ion concentration is. It will ask what the pH is. All right? Well, we know if we know the H+, we can calculate the pH because we have an equation. And so on around the bend. So we have very simple equations that relate H+ and OH values, hydroxide values and POH, simple equation, pH and POH, simple relationship, and pH and H+, a simple relationship. So here's what this means. If you know any one of these, you should be able to calculate the others. And I will tell you, it is common fare in chemistry, very, very common fare, for you to be given information about one of these, but it asks about another. And it can be confusing if you don't realize it. If it's asking about the pH, you're thinking acid, but then it's talking about a base. And the question would be, well, why is it asking me about pH if it's a base? Easy, because they're the same thing. So realize, anytime you have information and you can get it on this little cube here, then you should be able to go around the cube fluidly and convert any one of those to another. That is a critical core competency you will need for the next exam, I can assure you. On to the next slide if I can get there. Okay, so we worked a sample problem here, almost at the end of our review. Let's see, we work a sample problem. What is the pH of a base solution of hydride? Easy, it gives a hydride concentration. There we are. So since it asks about the pH, I'm going to choose to take it from, see, there's my star where I'm starting, and I put a box where I'm headed because it asked for the pH. So there's my star and there's my box. So I've chose to convert hydroxide to H plus using this equation. I know that relationship. And I calculated 8 times 10 to the minus 13. And then I chose to take that H plus concentration and take the minus log of it and go to 12.10. Does this make sense? Absolutely. Extract your data, analyze it, set up and solve it, and then test your answer. Test your answer. You know this is a basic solution, so the pH must be what? Greater than 7. And indeed, my answer is greater than 7. I feel pretty good about that answer. And finally, where we ended it was the relative scale, where we know that pH is considered neutral. And I did the derivation of that just to show you at a pH of 7, what that means is the hydrogen ion concentration is actually equal to 10 to the minus 7, because buried in this is a minus log factor. Okay, right. So pH 7 means it's 10 to the minus 7. Very, very small, but very, very significant. And finally, we looked at some examples of some common materials and what the approximate pH is for those materials. And with that, that's where we closed out the lecture. We will pick it up there in lecture 14.2.